Hi guys, welcome to our video on special factoring patterns. Our learning target for this video is I can use special factoring patterns to factor special cases of quadratic expressions. So as we learned today in class, whenever we have a quadratic expression, the first thing we want to look for is a greatest common factor to be factored out to make our expression more easily factorable. Sometimes, even after we factor one out, our expression may look very complicated. But another thing we can look out for are the two factoring patterns that we're going to learn in this video. The first factoring pattern comes from a perfect square trinomial. So it is what it sounds like. It's a trinomial of three terms and there's perfect squares in it. How do we get a perfect square trinomial? Well, what it comes from is when we take a binomial, such as the one shown right here, x plus 4, and when we square that, which means when we multiply it by itself. So if we take x plus 4 times x plus 4 and use our distributive property, we know that's going to be x squared plus 4x plus 4x plus 16. And combining our two middle terms, our like terms, we have x squared plus 8x plus 16. And this is a perfect square trinomial. Let me show you why. First of all, the big hint that a trinomial is a perfect square trinomial is that the first and the last terms are perfect squares. So x squared is a perfect square because that's x times x, and 16 is a perfect square because that's 4 times 4, okay? Now, you can probably tell that their square roots were the values in our binomial, x and 4. Now, the next thing that we check for in a perfect square trinomial is that the middle term is 2 times the first term, which in the first term in the binomial, which is x, times the second term in the binomial, which is 4. And that is true. 2 times x times 4 gives us 8x. Another way to think about this is when you multiply x and 4, you get 4x. And do you see when we were multiplying, we had 2 of them? Because they were the same. So we had 2 4x's, which gives us 8x. Now this pattern that was discovered is written down here in the box, a little more easy to look at. We put a's and b's in place of anything that could be in these binomials. So what we're doing is we're going to be encountering perfect square trinomials, and we need to identify them as perfect square trinomials. And once we do, we identify the a value and the b value, and we know that its factored form is just going to be a single binomial squared. So we can have one like we showed above with all positives, or there can be a negative b value, which means that the binomial is just going to be a minus b quantity squared. So let's look at example 4a. Factor completely. This one says x squared minus 10x plus 25. Before I start looking for a special pattern, I do need to see if there is a greatest common factor to factor out. This one does not have one, so I move on. I notice that my first term, of course, is x squared, which is a perfect square because that is just x being squared. My last term is 25. 25 is also a perfect square because that is 5 squared. So this one with a negative 10x in the middle is going to look like the one on the right because there's a negative. So we would assume that our factor would be x minus 5 quantity squared. And we just need to double check that the middle term would indeed be negative 2 times our first term, which is x, times our second term, which is 5. And of course, negative 2x times 5 is a negative 10x, so that did work. And this is our perfect square trinomial factored. So it's just the quantity x minus 5 squared. Okay, let's look at the next one. 9x squared minus 30x plus 25. So first we look for a GCF. There are no common factors between 9, 30, and 25. So we move on. 9x squared. That is also a perfect square because 9 is a perfect square and x squared is a perfect square. If we took 3x and squared it, we would get 9x squared. 25, where we've already encountered this number, we know that its square root is 5, so that would be 5 squared. And we see that our middle sign is negative. So again, this is going to look like the second pattern we have above. Assuming that 3x is our a value and 5 is our b value, this would factor to 3x minus 5 quantity squared. And you can just double check and make sure that if you took 2 times 3x times 5, that you would indeed get 30x. 2 times 3 is 6, times 5 is 30x. So we're good. All right, letter C, 4x squared plus 4x plus 1. All right, no GCF here. Let's go ahead and start doing square roots. 4 is a perfect square, so 4x squared would come from taking 2x and squaring it. 1 is also a perfect square. That's just 1 squared. And our middle term is positive, so we take these two values and we write them in a binomial, 2x plus 1 quantity squared. Double checking that this middle term does work out, we take 2 times our first term times our last one, and yes, 2x times 2 times 1, that is 4x, which is what we wanted. And our last one, 5x squared minus 40x plus 80. Hey, we can take out a GCF of 5 in this one. So let's do that first. When I divide each of these by 5, I end up with x squared minus 8x plus 16. Now you might be able to factor this without using the pattern because you're asking yourself what multiplies to 16 and adds to a negative 8. But the thing that we notice is that x squared and 16 are both perfect squares. So we think about what are their square roots, and the square root of x squared is x, the square root of 16 is 4, the middle term is negative, so that factor would be x minus 4 quantity squared, but we're still going to have that 5 out front. And remember, you can double check your middle term is correct if you take 2 times those two values we put in the binomial. 2 times x times 4 does give us 8x, so that is correct. And those are perfect square trinomials. Now, here's our second special case. It's called a difference of squares binomial. So this is 2 terms, and it is exactly what it sounds like, a difference of squares. You know, difference is when you subtract. So when we multiply opposite binomials, we end up with difference of squares binomials. So for example, x plus 4 times x minus 4. I call these opposite binomials because they're like the same thing, but one's addition, one's subtraction. So if we're going to go ahead and distribute this out, we'd get x squared plus 4x minus 4x minus 16. And when we have these opposite signs, it turns out that our two middle terms are opposites of one another, and they cancel each other out. So we end up with x squared minus 16. This is a difference of squares because we are subtracting, which means we're finding the difference of, we have x squared, which is a perfect square, and 16, which is a perfect square. So it's factored form, which is what we started with, x plus 4, x minus 4. Those are the square roots of the two terms. So here's your pattern down here. If you have a perfect square minus another perfect square, you take their square roots. One factor is their sum, and one factor is their difference. Let's check out example 5a. I have x squared minus 9. We see this is a binomial. The first term's a perfect square, the last term's a perfect square, and it's subtraction. So this is a difference of squares. We find their square roots. One would be x, and this would be 3. So the factors would be x plus 3 times x minus 3. Letter B, we have 9x squared minus 25. Again, we are subtracting. We are finding the difference. 9 and 25 are both perfect squares, so our roots would be 3x and 5. So the factors will be 3x plus 5 times 3x minus 5. Moving on to letter C, it's almost a little easier than letter B. It's 9x squared minus 1. Well, we already knew from letter B that already know that the square root of 9x squared is 3x, and we know the square root of 1 is 1. So this is going to be 3x plus 1 times 3x minus 1. Finally, in letter D, I noticed something I don't love to see. That's a negative in front of my x squared term. We definitely need to take a negative out. Looking at my second term, it's 12. So I actually can take this negative 3 out of both terms, which leaves me with x squared minus 4. And the whole purpose of that, as you see, it leaves us a difference of squares. So this is x being squared, and this is 2 being squared. So my final answer will be negative 3 times x plus 2, x minus 2. Okay, guys, I hope you have a spectacular weekend, and I'll see you Monday.